Welcome back to the session on Fourier integral representations. In the previous session, we discussed the Fourier integral theorem, which is a fundamental theorem in the study of Fourier integral representations. Now, here we shall discuss the Fourier integral representation of even functions and odd functions, and then we shall do some example problems. We have the Fourier integral theorem. If f of t is a function satisfying the Dirichlet conditions and integral from minus infinity to infinity modulus of f of t dt is less than infinity, then we can write the function f of t as integral 0 to infinity a omega into cos omega t plus b omega into sin omega t d omega, where a omega is given by 1 by pi into integral from minus infinity to infinity f of t into cos omega t dt, and b omega is given by b omega is equal to 1 by pi into integral from minus infinity to infinity f of t into sin omega t dt, where the function f of t is continuous at all points of t. We can write f of t as this integral. At the points of discontinuity, this integral value of this integral is the average of left hand limit and the right hand limit of the corresponding point of discontinuity. This is the Fourier integral representation. Now, suppose the function f of t is even. F of t is even means f of minus t is equal to f of t. If this condition holds, we say that f of t is an even function. Here consider a omega, which is equal to 1 by pi into integral from minus infinity to infinity f of t into cos omega t dt, where f of t is an even function. We know that cos omega t is always even. Therefore, this integrand will become an even function into an even function, means which will become an even, that is f of t into cos omega t is even if f of t is an even function, because cos omega t is always even. Therefore, this will become 2 by pi into integral from 0 to infinity f of t into cos omega t dt. By the property of definite integral, we can write a omega as 2 by pi into integral from 0 to infinity f of t into cos omega t dt. Consider b omega. Here sin omega t is always odd and f of t is even, means an even function into an odd function, which is always odd. For example, x square is an even function where x cube is an odd function. This product is x raised to 2 plus 3, that is x raised to 5, which is which is an odd function. Therefore, similarly, we have an even function into an odd function, means this product is an odd function. Therefore, by the property of definite integral, this integral will become 0, that is b omega is 0. In this case, f of t is integral from 0 to infinity a omega into cos omega t d omega. Now, consider f of t as an odd function, in which case f of t is odd, means this function, this integrand will become an odd function into even function, means which will become an odd. Therefore, value of a omega is 0, and this will become, here in b omega, the integrand is f of t into sin omega t. F of t is odd, sin omega t is always odd. Therefore, an odd function into an odd function, means which will become an even function. This product is an even function if f of t is odd. Therefore, by the property of definite integral, we can write b omega as 2 by pi into integral from 0 to infinity f of t into sin omega t dt, and f of t will become integral from 0 to infinity b omega sin omega t d omega. That is, if in this case, that is, if f of t is even, then the corresponding integral representation will become a cosine integral, and if f of t is an odd function, the corresponding integral representation of the function will become a sine integral representation. At the discontinuities, we can write the value of these two integrals as the average of left hand limit and right hand limit of the corresponding point of discontinuity. Now, we have to work out some example problems. First one is, find the integral representation of find the Fourier integral representation of the function f of t is equal to 0 for t less than or equal to 0, and e raised to minus t for t greater than or equal to 0. Here strictly less than, not less than or equal to, f of t equal to 0 for t less than 0 and e raised to minus t for t greater than or equal to 0. Hence, evaluate integral from 0 to infinity 1 by omega square plus 1 d omega. First of all, we have to write the corresponding Fourier integral representation as f of t is equal to integral from 0 to infinity a omega into cos omega t plus b omega into sin omega t d omega. Where a omega is given by integral from minus infinity to infinity f of t into cos omega t dt. Here the function is given in two intervals, two ranges. Therefore, we can split this total limit into two, that is equal to integral from minus infinity to 0 f of t into cos omega t dt plus integral from 0 to infinity f of t into cos omega t dt. This is equal to, here in this case function is defined as 0. For t less than 0 means t is from minus infinity to 0. In this case value is 0 plus integral from 0 to infinity. Here in this case f of t is defined as e raised to minus t into cos omega t dt. To evaluate this integral, consider cos omega t as we have e raised to I theta equal to cos theta plus I into sin theta. That is, cos theta is the real part of e raised to I theta and sin theta is the imaginary part of e raised to I theta. Therefore, we can write here e raised to I omega t as cos omega t plus I into sin omega t. Now, cos omega t means the real part of e raised to I omega t. Therefore, from here we can write this equal to integral from 0 to infinity e raised to minus t into cos omega t is real part of e raised to I omega t dt. That is real part of integral from 0 to infinity. We can combine these two, e power negative of I omega plus 1. Sorry, e power minus of 1 plus 1 minus I omega into t dt. That is equal to real part of integrate this, we get e raised to minus of 1 minus I omega t divided by minus of 1 minus I omega, because the integration is with respect to t. Therefore, the coefficient of t is 1 minus negative of 1 minus I omega between the limits 0 and infinity. This is equal to, when we apply the upper limit, this numerator will become e raised to negative of infinity, which will tends to 0. Real part of 0 minus, when we apply this lower limit, this term will become e raised to 0, that is 1 divided by negative of 1 minus I omega. That is real part of 1 by 1 minus I omega which is equal to real part of, we have to multiply both numerator and denominator of this one function 1 by 1 minus I omega with 1 plus I omega. That is real part of 1 plus I omega divided by here 1 minus I omega into 1 plus I omega. That is real part of 1 by 1 minus I omega into 1 plus I omega means 1 square minus I omega whole square, that is 1 square minus I square omega square. I square is minus 1, therefore, in the denominator this will become 1 square plus omega square. Now, we split into two terms, that is 1 by 1 square plus omega square plus I into omega by 1 square plus omega square. The real part is 1 by 1 plus omega square. Here in the expression for A omega, there is 1 by pi. In all these steps, we have to add 1 by, we have to include 1 by pi. Therefore, value of A omega is 1 by pi into 1 plus omega square. Now, consider B omega. We obtained A omega as 1 by pi into 1 by 1 square plus omega square, that means 1 plus omega square. Now, B omega is equal to 1 by pi into integral from minus infinity to infinity f of t into sin omega t dt. Here we can split this integral into two because the given function is in two ranges. Therefore, this is equal to 1 by pi into integral from minus infinity to 0 f of t into sin omega t dt plus integral from 0 to infinity f of t into sin omega t dt. That is 1 by pi into, in this case the function is defined as 0, therefore, this will become 0, and this integral is integral from 0 to infinity e raised to minus t into sin omega t dt. That is equal to 1 by pi into integral from 0 to infinity e raised to minus t into is this sin omega t can be written as the imaginary part of e raised to I omega t dt. That is equal to imaginary part of 1 by pi into imaginary part of integral from 0 to infinity e raised to minus t into e raised to I omega t, means e raised to negative of t, minus 1, negative of 1 minus I omega into t dt. On integration, we will get this equal to 1 by pi into imaginary part of e raised to negative of 1 minus I omega into t divided by negative of 1 minus I omega between the limits 0 and infinity. When we apply the upper limit, this term, this numerator will tends to 0 because e raised to minus infinity tends to 0, and the when we apply the lower limit, we get 1 by pi into imaginary part of 0 minus when t equal to 0, this is 1 divided by 0 minus 1 divided by negative of 1 minus I omega. That is 1 by pi into imaginary part of 1 by 1 minus I omega, that is 1 by pi into imaginary part of 1 plus I omega divided by 1 square plus omega square. As in the previous case, we have to multiply the conjugate of 1 minus I omega in the numerator and denominator. We will get this, which is equal to 1 by pi into imaginary part of 1 by 1 plus omega square plus I into omega divided by 1 plus omega square. That is 1 by pi into this, the imaginary part is omega by 1 plus omega square. This is the value of b omega. That is b omega is 1 by pi into omega divided by 1 plus omega square. And therefore, we have to write f of t as f of t is equal to integral from 0 to infinity. A omega is 1 by pi into 1 by 1 plus omega square into cos omega t plus b omega is 1 by pi into omega divided by 1 plus omega square into sin omega t d omega. That is, here 1 by pi is common, which can be taken outside of the integral. We get 1 by pi into integral from 0 to infinity. 1 by 1 plus omega square is also common into cos omega t plus omega into sin omega t d omega. This is the Fourier integral representation of the given function. Now, we have to evaluate this integral. Here, the function is defined as f of t equal to 0 for t less than 0 and e raised to minus t for t greater than or equal to 0. Therefore, t equal to 0 is a point of discontinuity. In this case, we can write the value of this integral as the average of right hand limit and left hand limit at t equal to 0. Now, the right hand limit is f of 0 plus, which is equal to limit a tends to 0 where a is greater than 0, f of 0 plus a. This is equal to, in this case, f of 0 plus a means f of a quantity greater than 0, which will become in this case therefore e raised to minus a. A tends to 0 means this is 1. That is, the right hand limit at 0 is 1, and the left hand limit f of 0 minus is limit a tends to 0. This is the definition of left hand limit, where a is less than 0. Sorry, here a is always greater than 0. F of 0 minus a, here 0 minus a, which is equal to, this will become in this case, because minus a is negative, therefore, for all values t less than 0, f of t is defined as 0, therefore, here it will become 0. The average is 1 by 2 into f of 0 plus plus f of 0 minus, which is equal to 0 plus 1, that is 1 divided by 2. Now, at t equal to 0, the function is defined as 0. Sorry, at t equal to 0, we can write this expression as integral from 0 to infinity 1 by pi into 1 by 1 plus omega square into cos, when t equal to 0, this is cos 0, that is 1. When t equal to 0, this will become 0, 1 plus 0 d omega, which is equal to, the corresponding value is 1 by 2, that is integral from 0 to infinity 1 by pi can be taken outside, 1 by 1 plus omega square d omega is equal to 1 by 2. That means integral from 0 to infinity 1 by omega square plus 1 d omega is equal to pi by 2. This is the value of this integral. We can verify this value by actual integration. We get integral 1 by omega square plus 1 d omega is tan inverse omega between the limits 0 and infinity, that is equal to tan inverse infinity minus tan inverse 0. That is tan inverse infinity means pi by 2, tan inverse 0 is 0, that is the value is pi by 2, which is true. Therefore, using the Fourier integral representations, we can evaluate some integrals. With this example, I conclude this session. Thank you for watching this session. Have a nice day.